Hello everyone, I'm Neha Swedi. I am a second year environmental engineering student at University of Vermont. I am currently working on the school project where we are trying to explore the idea of using process glass aggregate in the transportation projects, specifically as a substitute to sand borrow in road subbases. Sand being the second most consumed resources in the world is depleting rather rapidly. On the other hand, glass waste is rapidly increasing, with almost 70% of them ending up in landfills. Using processed glass aggregate not only provides us a way to lessen the burden on a depleting natural resource, but also helps us divert waste from the landfill and gives us this amazing opportunity of converting waste into an asset. Despite the potential of glass waste of processed glass aggregate, the widespread use of PGA in construction is still very much limited. Primary reason behind this are deleterious materials. So when recycling glasses are processed in the recycling facilities, the end product is not only the glass aggregate, but different types of other recyclable materials like plastic, paper, food matter, metals, etc. that are processed together with the glass. At present, the only reliable method to determine these deleterious materials is visual inspection and manual picking, which is not just tedious and unreliable, but it's practically impossible. So, our main goal of this project is to develop straightforward and reliable methods to quantify these materials in PGA and establish PGA as a sustainable construction material. So for that purpose, we have developed three distinct tests: magnet test, furnace test, and float test. So, uh, and then we have developed uh, two protocols from the combination of these three distinct tests for different purposes. So the first test is the combination of magnet and furnace test. We carry out magnet test in our samples that gives us the total amount of ferrous metals present there. And then we burn the leftover materials in a muffle furnace at 550 degrees Celsius and obtain the removal of the remaining deleterious materials. The aggregate of these two tests gives us the total deleterious materials in PGA. Then protocol 2, which is float test, basically consists of floating the materials, allowing all the materials that can float to float on the surface of water. Then all of those floated materials are scooped out. They are visually examined for plastics, sorted as plastic types and different colors of plastic. Similarly, the leftover portions are also visually examined to pick any plastics or plastic looking like materials that might not have floated during our test. To validate the efficacy of these results, we prepared our lab manufactured process glass aggregate by crushing clean glasses. We took 98% of that glass, 0.4% of office paper, 0.4% of newspaper, 0.4% of PP plastic, 0.4% of HDP plastic, and finally 0.4% of peanut butter. Each of them are the representation of the real deleterious materials we find in the real PGAs. We set the target measurement on the basis of the quantity of the deleterious materials we put in and the purpose we designed the protocols for. For magnet test, ideally the magnet constituent in the clean glass is 0%. For furnace test, we are expecting the entire deleterious material to burn. Therefore, we have 2% of our target measurement set. For float test, we expected all the plastics to float, uh, hence 0.8%. So for result one, protocol 1 and 2 test on our lab manufactured PGA, we can see in table 1 that we have our metal content as 0.03%. We believe this is because clean glass has some metal additives while manufacturing. The furnace test removed 1.88% of the materials. Likewise, for float test, we could retrieve all the plastics that we put in and nothing floated. No other materials floated except for plastics. Hence, we could conclude from our study that our two protocols are pretty effective in determining the overall deleterious materials and plastic contents respectively. Then, after validating our protocols with our lab manufactured PGA, we carried out a protocol test on 5 different batches of CSWD samples. Table 2 is the result for Protocol 1 and Protocol 2 tests on around 120 samples tested, 60 samples each for Protocol 1 and Protocol 2, all on the samples that we received from Chittenden Solid Waste District County, Vermont. For magnet test, in Table 2, we recorded an average of 0.12% metal content and 2.86% of deleterious materials removed from furnace test. The overall deleterious material was found to be around 3% from the sum of magnet test and furnace test. Likewise, from the float test, 0.07% of the material were determined to be plastic-like materials and 0.07% of plastic-like materials were recorded in the leftover. The sum of these two results in 0.14%, which is the total plastic content present in our samples, which falls way under the specification limit of 1% set by B-Trans for specific plastic limit. Then a comprehensive plastic analysis was conducted on one of the 5 batches of samples using FTIR, where the results were analyzed using hit qualities, spectrum analysis, and visual confirmation. Table 3 shows us the various types of plastics that were detected in one single batch of CSWD PGA. So overall, in our conclusion, we conclude that Protocol 1 and Protocol 2 are operationally reliable. Deleterious materials in PGAs differ from dates to dates, from piles to piles, from locations to locations. And our major finding was that uh, the plastic content in the PGA batches that we analyzed was minimal. So this is the work we've done so far, and for our upcoming work, we are planning to conduct a geotechnical property test on PGA and compare them to sandboro materials, and then finally perform an economic and environmental analysis of PGA to assess their suitability as a viable construction material. Thank you.